Okay guys, welcome to our molecules lab. And before we jump into toothpicks and gumdrops, we have to review our bonds here a bit. And this is tricky stuff and it kills me that I can't teach you guys in class, and I really hope that I can be as clear as possible with this process here. So you can pause this video and pull out your doodle notes from your science notebook, or you can follow along with my screen here. But if you remember ionic and covalent bonds, our ionic bonds, those were a metal and a non-metal. And valence electrons are always donated. So we had sodium, we had chlorine. And let's see if we can remember what happened here, right? So if we refer to our periodic table, sodium has one valence electron in its outer ring, and chlorine has 7. And full rings are happy rings. We want to fulfill our octet rule. So sodium, he decides, I'm going to donate my electron and give it to chlorine. Now, sodium, he donates. And anytime you give something away, you just feel so great. Like I went through my closet, I pull out all the old clothes that I don't wear, don't fit anymore, and I decide to donate them, and I feel so great, right? So that makes me feel positive. I gave away, I feel positive about it. And remember, my memory trick was a positive is a cation, right? Cats give us positive feelings, right, Samantha and Trinity? Lots of positive feelings for the cats. Chlorine receives the electron and has its full ring now. Now, chlorine, have you ever met someone who just has the gimmies? Gimme, gimme, gimme. I just want. Okay, so chlorine is always taking the electron to get a full outer ring. And because they've always got the gimmies, they've kind of got that negative vibe, right? So chlorine gets and is now negative. And then the memory trick was a negative is an anion, and anion to me always sounded like onions, and I don't like onions that much, so I feel kind of negatively about onions and anion. Okay, but now we've got Mr. Positive Sodium, we've got Mr. Negative Chlorine, and opposites always attract, just like in a Hallmark movie. Opposites attract and they form a perfect match. My positive, my negative, ka-ching, and we get an ionic bond of sodium chloride. So that's our quick review on ionic bonding. Over to covalent. Covalent bonds always are a nonmetal and a nonmetal. Okay? And covalent bonds are a prefix here of co, like if we cooperate, if we co-teach, if we cohabitate, that's always doing something together. So covalent means we're going to work together here and we're going to share the valence electrons. Okay, so in covalent bonds, our nonmetals are going to share our valence electrons so that everyone has a happy outer ring. Okay, so if you remember from our lab with the beads, and you guys would slide your beads around to make those bonds take place, that's what we're going to be doing in a bigger way today. Okay, so covalent bonds, we're sharing. Okay, so then we're going to look more at that in a second, but really quick, let's remember this important thing right here, that a compound is 2 or more different elements bonded together, and a molecule is 2 or more atoms bonded together. Okay, and they don't have to be different. O2 is a molecule, but it's not a compound, it's just 2 oxygen, okay? So that's our compounds and our molecules. So keeping that in mind, we're going to head over to our textbook here, and we're going to read a bit together. Okay, so chemical bonds forming. Why do fireworks... Oh, I'm on the wrong lesson. Fast forward, please. Bloop, 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 bloop. Covalent bonds. There we go. Can you tell that I, as your teacher, was reviewing? All right. Suppose that you and a friend are collecting the U.S. commemorative state quarters. Do you remember those? Is that before your time? Collecting whatever you want to collect. Your friend is missing the Utah coin to complete her collection of all 50 states. You not only have a complete set, but you also have an extra coin of Utah. You gave it to your friend to complete her collection. As a result, you both have a complete set. And I have a complete set of those quarters all stuck into some state map board somewhere. Now, how are those state quarters similar to what happens when an ionic bond forms? Imagine that your friend has a complete set and that you're missing Utah. How can you both have a complete set, even if you both cannot have a complete set at all times? In this case, having a complete set is similar to what happens when another type of bond is formed between atoms. What do you think happens in this case? We share. So what happens when two hydrogen atoms are near each other? Each hydrogen atom, look over here guys, each hydrogen atom has only one electron, which is found in its first energy level. This energy level can hold a maximum of 2 electrons to become stable. Why doesn't one hydrogen atom simply give up one of its electrons to the other atom? If it did, what would the hydrogen atom become? Rather than give up their one electron, both hydrogen atoms can achieve stability by having 2 electrons in their first energy level. If the 2 hydrogen atoms share their electrons, they each have the configuration of helium atom. So they share, how nice of them, and they form the helium atom. The strongest chemical bond, looky there, woo, so important. The strongest chemical bond that forms between atoms when they share electrons is called a covalent bond. The electrons shared by the atoms are attracted to the nuclei of both atoms. The atoms must stay together to complete their outer energy levels. You know that atoms that are held together by covalent bonds are called molecules. If Na and Cl are held together by bonds, then why don't they form a molecule? What are they called instead? Thinking back to what Miss Vigil just talked about a minute ago, Na is a metal, Cl is a nonmetal, metal, bonds, cation, anion, opposites attract, what are they called? Ionic bonds, an ion. Okay, so now up here, electron dot diagrams. The top part of the diagram below shows all the energy levels of 2 chlorine atoms that form a chlorine molecule. In chemistry, the inner energy levels are often omitted from drawings because they don't change when the elements bond. But notice that in the bottom diagram, down here, the valence electrons are shown as dots. Sorry, I meant there. Around the chemical symbol. These simplified drawings are called electron dot diagrams. The shared pair of electrons is shown as a single straight line that connects the 2 atoms in a covalent bond. After bonding, how many valence electrons will each chlorine atom have? Okay, so what this is saying is, do you remember our periodic table in the classroom? If you lifted the flap, you would see this electron configuration for all the electrons. And you remember how some of our elements, like gadolinium, had a gajillion of these rings and these atoms? They are simplifying it because what determines how atoms bond? The outer ring only, the outer ring only. So that's why down here, they are simply showing you with dots around the symbol how many valence electrons are in that outer ring. So Cl has 7. If they choose to share, they all have 8. And here's something that's going to come in handy. Right here, can't highlight it, so just look at where my mouse is. This line there, it represents 2 valence electrons being shared. So right here, that's a share. Those 2 are being shared, and my line signifies that bond. Okay? Atoms can share more than one electron. For example, carbon has 4 valence electrons. It needs 4 more to complete its outer energy level. Oxygen, so here's carbon with my 4. Oxygen needs 2 electrons to complete its outer energy level. Both atoms will be complete if carbon shares a pair of electrons with each of the 2 oxygen atoms to form a carbon dioxide, CO2. So you can see this bond that's taking place here. This type of bond is called a double covalent bond. The 2 double covalent bonds in carbon dioxide can be written as C bond bond O bond bond C. So 2 lines, and each line represents 2 electrons. Nitrogen, N, has 5 valence electrons, so an additional 3 would complete its outer energy level. When 2 nitrogen atoms combine with one another, they share 3 pairs of electrons. This is called a triple covalent bond, which can be written as N, 3 lines, N. Okay, so that's all elaborating this part here. Crazy, all of the bonding. So now, over to our lab. Right here, okay? So we are now in our Google Doc that you copied from the last video. And our essential question here is looking at how models are used to depict simple and complex compounds. So, imagine yourself shrinking smaller and smaller like a hero of a comic book movie. First, the world would look enormous, with gnats like buffalo. Suddenly, you are so small that you can see the tiny materials that make up everything around you, atoms. Side note, when I was your age, the movie that illustrated this was Honey, I Shrunk the Kids. For your guys' era, what would illustrate this is probably Ant-Man. So just imagine shrinking, shrinking, shrinking to seeing atoms in their purest form. An atom, the smallest possible unit of matter, is made of a single element, hydrogen, mercury, gold. Atoms can bond together then to create our molecules. Atoms form bonds through chemical reactions. They can form molecules that have simple or complex structures. If a molecule includes 2 or more different types of atoms, it's considered a compound. Some compounds have properties that are greater than the sum of their parts. For example, a water molecule is H2O, made up of 3 atoms, 2 hydrogens and 1 oxygen. Separated, they would float around in the air, and when bonded, you can float on them. Definitely took my brain a second, but H2O is water. We float on water. Got it. The compound pictured above is vitamin C, something we all should be taking right now with this virus going around. And vitamin C is made up of carbon, oxygen, and hydrogen. The model on the left is called a ball and stick model because each type of atom is a colored ball and the bonds are the sticks. The model on the right is known as a Lewis structure. It represents the bonds with a line, just like we saw on the previous textbook page. But notice that carbon isn't marked anywhere on this model. The scientists who use these models know that carbon would be found at each unmarked corner, and so they don't label it. So that's cool for them. My brain was like, why wouldn't you mark it? I want to see where everything is. But then I realized that this looks really, really complex, and simplifying things is good in science. So models are useful tools for viewing structures that are too small to see without special equipment. In this lab, you will be creating simple and complex models of different molecules. So guys, here is your first step. You have a Ziploc baggie that has gumdrops and marshmallows and toothpicks in it. And what I need you to start out by doing is I need you to separate all of your treats by color. So make different stacks with different colors on them, and then you will move on to my next video. See you there.